I'm Stephen Foskett, the organizer of Tech Field Day, and the video you're about to watch is a Tech Field Day presentation from November of 2016. We have invited a panel of independent writers and speakers from across the internet and around the world to join us here in Silicon Valley to meet with various companies, discuss their products, and learn about their technologies. Right now, you're going to learn about Igneous Systems. You can find out more about them. You can find them on Twitter, Igneous.io. You can go to igneous.io. And if you'd like to learn more about this event, just go to techfieldday.com or view more videos like this at youtube.com/techfieldday.
I'm Jeff Hughes, CTO and co-founder of Igneous, and I'm back. And I think based on a lot of the tweeting, this will be the nice meaty chunk of like, okay, how have you guys actually built a Datapath? What does this thing actually look like on the inside? So please feel free to just interrupt, understand really what's going on here. Now, as folks who have built sort of data products in the past, the first thing you might be thinking is like, yeah, we built a new Datapath, right? Like a little success kid here. But we got enough scars to say, like, why did we do that? Why did we actually think that we should go build another storage layer out there in the ecosystem? And it was something that we did not take lightly. In fact, we took the first 6 months to really understand, was this the right thing to go do? And so I want to walk you through a little bit both what our thinking was within that model and then what we did build and kind of understand that. So again, feel free to interrupt me on this. All right, obviously there is a ton of great open source software, open source storage software out there. And another quote that was, I can't remember if it was on the A16Z podcast of, software businesses today are really about operationalizing software, not necessarily just building new IP in the form of software. All of it's built at this point in time, so why wouldn't we use that? So we looked at a lot of open source software, but one of them was the one that stood out to us as most interesting, and that was Ceph. And I'm curious if anyone in the room actually has experience with Ceph at all. Great. So we liked a number of things about Ceph. We actually really think it's a great product, or at least piece of open source software. One was the crush algorithm, and you can go read about this a little bit more, but it's this concept of deterministically laying data out across a distributed system. Is that they have a great model for how do I lay out, billions of things across, thousands, tens of thousands, hundreds of thousands of devices and still know where it's all at, and in a very lightweight and efficient way. And the key to that is really the crush algorithm. They had this great model of, they call it their object storage daemon abstraction, but you can imagine with the ratio perfect architecture, you want a swarm of things figuring out how to repair and keep things sort of in a high integrity fashion and scrubbing things in the background and all that sort of stuff. And so the idea of moving more of the kind of keeping things healthy down to the individual drive level was really interesting, and that's something Ceph really introduced in that world. And then they also had this idea of immutable data. You don't ever overwrite anything, you always just append more. And as somebody who's built storage systems before, it's really both useful for the media that's out there today, as in Flash and not wanting to wear level things and various stuff like that, as well as the new spinning media that's coming out there with SMR. Having something that appends all the time as opposed to overwriting things is huge and really nice. Now, okay, why did we not select this? Because the short answer is that we don't use Ceph underneath. Really, it was that our operational experience was that Ceph didn't have enough fine-grained control over how you would want to lay out the data or how you might choose to do things operationally. And as somebody who was building a business around the operational aspects of this, we found that some of those things were just not going to be fit for the ways we had seen managing large-scale data, particularly content-heavy data like we've done before. Is that, I'm curious to your experience on the management plane side?
No, I mean, I don't have definitely as much experience as you do on that, but I mean, I would agree. I think it's probably way restrictive for what you want to try to do.
Yeah, it's very, very prescriptive about how they want to do things. And so we could have ripped a lot of that out, but it would have gone against the grain of the code and how it was designed, because the last piece was it was really designed around scaled out block, and we weren't necessarily going after that. We're more on the content storage S3 kind of object side of things as opposed to fixed styles file systems out there. And a lot of those decisions come back to, hey, they're supporting a huge installation at DreamHost and various other places like that. So, all right, so we built it from scratch. Our focus was really on capacity and performance. Note that that's not about IOPS, it's more about throughput and that sort of stuff, but we can do that as well. It's very Ceph inspired, so we borrow a lot of those same concepts of immutable data path and some of the crush pieces. And really, it was just taking a lot of the things of both our founding team and a lot of the folks that we've hired, where we've built file systems from scratch that are in use at tons and tons of data sites at this point in time. So,
did you look at using Swift instead? I mean, Swift seems a little more logical than Ceph.
It does. Swift, it can work for certain things. I think that there was a lot more that we wanted to do with our data path that we didn't see a logical place to put it into the Swift architecture as well, is that it was not really flexible enough. And we also saw that particularly when we wanted to scale things down to the nano server, Swift is pretty resource intensive and has a lot of tunables that you have to go do to get things right for every environment. And so it just didn't fit well with what we were looking to go do. Do you use Swift?
Yeah. I mean, we use SwiftStack's version of Swift.
Okay. Let me walk through what our basic breakdown of our architecture is. Kind of the very high level is 3 levels. So we've got an object layer, and really that's responsible for things like access control, namespacing across this whole fleet of infrastructure, the metadata. So when you assign various pieces of metadata, and really the kind of indexing of all the content that you have across that. So this terminates the front end and whatnot. We have then a kind of a logical layer of our resilient store. And you can think of our resilient store as very similar to what you'd see in Ceph. So this has got our layout decisions, erasure encoding that we use to spread the data out across the number of devices, and it handles all the sorts of things of resiliency around repair and rebalance, adding new infrastructure in, removing things that are dead, and so on and so forth. And then at the very bottom, the beauty of having software right next to the drive is that you can do some very interesting things around, hey, what we do for data placing on the drive itself, device health, all sorts of things that, since you have a little bit of logic there, there's actually a lot of great intelligence you can put right at the disk layer itself that's pretty interesting. So the question that always comes up is, how do you lay this data out across there? How do you get the resiliency that allows us to offer this really as a service? And this is again, an outcome of many years of seeing systems out there in the field and how to run it. So we call this deeper. It's the distributed erasure encoding with prioritized repair. We have some patents on this. The short answer is we lay out in a very wide stripe. So this is 20 plus 8 effectively. And let me talk through this a little bit. So effectively what we do is for every 20 blocks out there, we generate 8 erasure encoded blocks, which are a combination of local repair codes, and I'll talk through a little bit more of that, plus Reed-Solomon. So you could consider this like 20 plus 3 if you just considered Reed-Solomon, which is very similar to what either a RAID DP uses or something like that. But then we also scatter in a number of these local parity blocks. And this is something that we actually saw from folks like Microsoft and Facebook. You can go look at some papers around LRC, which is this idea of if I lay out a big stripe like this, the problem comes when I do a repair, I have a huge I/O expansion. If I lose just one block, I have to read 20 blocks to replace that one block. And that becomes really expensive for just the usual case of losing a single device. So instead, you chunk little sections of, in this case, 4 plus 1. So you have an encoding block for every 4 blocks in this picture. And now, if I lose a single device, which is the most common thing out there, I'm only having to read 4 other devices to reconstruct that data. And so the I/O expansion in those cases is greatly minimized. The result of that is that we can very predictably have our sort of background tasks be not very impactful, even though we have pretty good efficiency by having this very wide stripe out there.
You said there's a network switch inside of the JBOD. What's that capacity look like? Because isn't this pretty network intensive?
It can be. So it's a full non-blocking within that. So, but the key is that we can actually do some very interesting things where we can actually, the distributed aspect is that we can repair across a series of these nano servers. So we have the bandwidth in the CPU across the set of nano servers to chain together, and there's a patent we have on that, to actually do the repair kind of in a peer-to-peer fashion, if you will. And so it is network intensive, but a lot of it can actually happen within the non-blocking switches, and even across the top of rack, it's not that big of a deal.
Okay, so I mean, but general hydration of a file again, or of an objective again, I mean, if it's spread out across 20, I mean, what's the general, once you have this thing fully populated, 200 terabytes, what does it look like from a back-end capacity? I mean, how much, I guess, are you using sustained bandwidth to actually rehydrate those objects again?
So one, in the usual case, it's a direct mapping of front-end output to input. We don't have a lot of network overhead, if that's what you're thinking. So we can directly say, like, hey, if I need to read across 20 devices to read concurrently across all of those, I can bring those all up in parallel and into a front-end node. So we can saturate easily any network that we put on those chassis just because we have enough devices in there. So is that kind of?
Yeah, no, and I didn't think about that. Then you have the front-end node that you can actually then do the file, the file read from, or the object read from.
That's correct. So usually on the normal read-write path, we're going to go through a top-end kind of stateless compute node that can do either reconstruction on the way back out as you're assembling this into a stream, which is what you would see on the front side of it.
Yeah.
So that happens kind of at that object layer, is that you've got the ability for any one of the top-end nodes to do that reconstruction because they can just read direct from any of the bottom half sort of nodes. And so that's why things like QoS are kind of important in our workflows and that sort of thing. So the result of this, since it's not necessarily that obvious, is that we can sustain up to 4 to 8 concurrent failures. And again, that's concurrent. So we're always managing this and enacting the ability to essentially eat into the local capacity as we might be able to rebuild and fully bring things back up to full resiliency. And really, we came to this by, hey, our experience says that 2 to 3 failures is probably what you need. Let's double that and ensure that we can always recover in these scenarios, because it's always going to look a little bit. We never want to be in the situation where, as offering a service, we have to start having the conversation about protection.
So define failure in this case. That could just be a bad sector on a single disk, or multiple, or the entire disk failure?
Yeah, I mean, you could think of any particular byte, how many things around it could fail on that. So yes, certainly things like latent sector errors and whatnot could be one of those failures. That said, we're able, with the drive right there, when a drive is idle, it's going to go spin up and be able to do scrubbing of what's going on behind the scenes. So we catch most of those, but certainly those can factor in here as well.
So are you doing this, just to be clear, are you doing this erasure coding at a block level on the drives, or are you doing this at an object level so you could then redistribute it across whichever drives for every individual object?
So we have a very clean layer where we do it kind of, the object layer talks to just what it thinks of as one big scaling resilient store. And so we can redistribute the object data across to any device whatsoever. So when it comes down to the very back end here, you can think of this as just a highly distributed kind of erasure encoded layout. So we spray the data in many different ways. It doesn't have necessarily orientation to the objects that are on the top half, because we'll group things together if they're small or cut them up if they're big. So there's a many-to-many mapping there from an object to layout perspective. Really, we optimize that around the performance aspects of it.
You're not linking it directly to the underlying specific drives as well, which means that it reduces the incidence of hotspots if you have a certain number of objects.
That's correct, yeah. So we go for, and a lot of this learnings came from Ceph. We're not, just geniuses about this. They showed very clearly that if you uniformly distribute things across the whole array, you're going to get a lot less hotspots and that sort of stuff. And even a lot of times those hotspots that you might get, you can solve with caching in various ways as well. So. And then I mentioned this a little bit, but some of our learnings that we got out of this were really around, hey, when you have concurrent failures, the most important factor is actually to get to the point where you're not any closer to data loss. And so we call it prioritized repair, which is we ensure that, hey, let's say we did have 4 concurrent failures. We're going to repair, some pieces of data might only have been hit by 1 or 2 of those failures, but some of them might have been hit by all 4 of those failures when you consider that this is spread out in a very wide fashion. We go and spend all of our resources, which is resource intensive, on getting those ones that are most impacted up to full resilience as fast as possible. And so we prioritize that, and that's part of the benefit of both we can go do that because this is more this flat network where we can choose how to optimize our resources as opposed to more bottlenecks that are involved in the process. And then I mentioned a little bit about distributed repair as well, where we can actually not involve kind of top-end devices at all. We can have all of these little nano servers participate in a distributed repair, and therefore, as we add capacity, we're adding the ability to repair as well. So there's none of these games of like, oh, how much CPU am I using on repair versus my activity or whatnot. Our hardware platform allows us to do some very interesting things from that perspective. Any other questions on kind of the erasure encoded aspects of this? All right. Now, I want to talk a little bit about the high-level aspects of this too. So we went all the way down to the bottom of like just how do we make sure this thing is repairable and resilient, which is always the first question as a startup saying I want to store your data. You always got to explain, look, I'm not going to lose your data, and here's why. The other aspect is what were our goals for building this thing and kind of what were we directed towards? And really the architecture was informed by this idea of we wanted to independently scale read, write, and capacity. And that is a lot different than what's out there. A lot of times you have a coupling of one or two of these things together just based on how it's architected. And so just to walk you through a little bit of that, well, first of all, and then the other aspect is that we wanted to be able to flexibly use SSD, hard drives, PCI if you need to, or lower latency flash and that sort of stuff. But let me walk you through probably one of the key aspects that you see in file system design is really around journaling. Is that almost all sort of data stores of various kind, whether it's Swift or Ceph or even the stuff you see in NetApps or pick your favorite thing. They all have some sort of journaling, which is really about the write throughput. And so if you look at this, journaling usually comes in one of two forms. You either have what I would think of as kind of a write-back model of journaling, which is, hey, maybe call this layer flash or an NVRAM of some sort. I'm quickly able to make a write. I journal it and ensure that it's resilient in some form, and then at some later date, I'll drain that out to my capacity. And that's a very common model. No problems with this. You could very much think of this as like the NetApp, NVRAM style of things. There's some other aspects of that as well, or other products that go do this. The other that's most common actually in a scale-out model is what you'd think of as a write-through model. So you put a little bit of journaling on every device that's out there. This is what happens in Ceph, for instance, is that with every device that you have out there, you have some journaling media sitting right next to every bit of capacity. And now you've coupled kind of the amount of write throughput you have with the amount of capacity you have. And so these are the sort of things that we were considering of how do we architect this such that we could actually take the best of both of these worlds. We could say, hey, I want to scale my journal or my write throughput independently from my capacity or my read access, how fast I can read things independently, because there's just unpredictability in all three of these things in a lot of use cases that are out there. So let me walk you through a little bit how we think of that, and you guys can tell me whether this matches or not. With the key of our architecture is that we have this kind of network-centric approach. We can actually blend, some faster media with some slower media potentially, or what we use for journaling versus what we don't, all in a single box and transparent to the end customer at that point in time. And then if you look at it, there's a lot of processing that goes on to go lay things out across that. So let me walk you through how we do this. Is that same picture, but just a little bit more blown out that I showed before, is that, hey, first you have your protocol endpoint. That just kind of does your normal termination. From there, we have some sort of ingest aspects of this where, hey, I'm going to go journal that an action happened, and then I'm going to drain things out. So you can think of this as very much that kind of write-back journal format. But the key aspect that we can do differently is that we can actually separate out the set of devices that are used for journaling versus capacity, and we can scale those independently in a very granular fashion depending on how we need to go do this. And so we've actually taken the blend of both the ability to do that kind of write-back journaling, but in a scale-out fashion, and granularly bending on the workflow that you want to go do. This takes a little bit to absorb, but I'll pause there and see if that makes sense. All right, here's the key is that we can scale all of these processes in blue, which are really, if you think about it, where read comes from is how do I go understand where something's at and then pull it off of the capacity where it's at. That's really the top-end CPU. So we think of read access as a CPU plus caching problem in a lot of ways, because either you're going to go hit something and you want it to be on fast media, or you have it cached in memory somewhere. So it ends up being a computation problem more or less. So we can linearly scale the amount of CPU that we have in our architecture by just scaling out that x86 stateless model of top-end compute. We can obviously scale the size of our journal and therefore how fast we can accept writes by just scaling the set of devices that we have underlying for journal media. And then we can obviously scale capacity in which of those we choose to go build at the bottom half of that.
So if I'm buying your service, are you sending in my I/O profile changes? Are you sending me different types of drives then to exchange, or?
So today, this is how we built the architecture. I think you can see the trajectory of where this goes. We ship all just spinning media for all of these layers today. And the reason why we did that is we said, look, we need to make this work really well on the lowest class of media first before you go hit things at a performance, IOPS scale basis. So the model works really well, and in fact, we've got internal test points that show that. But today, it's uniform across what's inside.
Okay.
There's some fun things coming up there. So that's kind of where I'll leave it right now, which is the stay tuned. I think you can see where we can go with this. Today it's about S3, which runs on spinning media well, just based on the workflow that's there and whatnot. It's large transactions, chunky data at that point in time. We had a big focus on resiliency and flexibility to go do that, the flexibility aspects, and then there's some more things we got coming in the future that will take advantage of that architecture a lot more. Any other questions about not just this, but any of the material we've shared today?
So there's a question from Twitter, and it's basically they're saying one of the main reasons customers are not happy to move out to the cloud is the paranoia about the security and the control piece. So you've already described that you don't allow inbound connectivity. You're pushing, you're going outbound with a port 443. But how do you tackle that objection handling piece with those paranoid customers, and how do you give them the kind of security that there's no way that data is going to get exfiltrated over that connection and so forth?
So there's a couple of key aspects from a technology perspective that we do this, but I think of security of both the technology, the process, and the people that are involved. And so we think pretty seriously about exactly this question, because we do see the opportunity of, hey, there's things that people have proprietary and want to keep local. So for instance, we ensure that we have no visibility of the contents of the data, and we have a large separation of concern, particularly within the way that we've designed our services internally. So that's the technology aspect. The other aspect is that we have a strong chain of control around signing particular operations and how we would go do that, and signing our software such that we can show, hey, a proof of work that we actually distributed this command or distributed the software that was associated with it, because, hey, look, those are your key aspects of control and what goes on in this process. And so there's process, there's technology, but it's an in-depth conversation that we have, with CSOs and whatnot. But what I've found is when I've talked with CSOs, that they find this very appreciable because they want to go take advantage of the cloud, but they need something that fits within their current policies. It's not that they're actually afraid of the cloud, it's that their policies don't apply well to kind of the paradigms of, hey, I can just lift and shift something up to the cloud. So they can do it within their network, which is really, it's usually kind of perimeter focused and within their environment, start taking advantage of some of these new cloud native models, and then, either use it as a stepping stone or that's where they end up.
Can they push, say, logging of all operations on the system to their own syslog type platform, Splunk, et cetera, et cetera?
Certainly can. We haven't had any requests for that today. So, but yes, obviously some sort of audit format of what's going on there. We can generate those logs, and we do for when we do internal debugging and that sort of stuff. But we don't necessarily, and we get operational views of it back to us so that we can profile what's going on. But all of the content is obfuscated.
Cool.
So I heard mention of performance and availability SLAs. What are those?
So you think of it as standard cloud 5.9 sort of thing, right? Our upgrades are all non-disruptive from that perspective. The architecture buys us the ability to have high availability on what's going on there. Obviously, from minimum configuration standpoint, you're at like a 1+1 on the front end side. So we can only really promise kind of like 10 gig throughput to the Datapath at that point in time, just on the way we spec it today. But from an availability perspective, we're up as much as the data center that we're in, and then we can also offer, obviously, DR solutions across sites as well.
So 5.9's in what window?
Year window, which is usually an hour of outage, sort of.
Okay, year window. What's the penalty?
That's a good question. I don't think we've.
That's the late
What was
penalty.
that? I didn't hear.
So what's the SLA breach penalty?
No, we do not. If you look at, there isn't any at this point in time. We are working with customers. Nobody asked us for that sort of a
Nobody
stuff.
asked you for an SLA penalty?
They have not asked for an SLA penalty, quite honestly. And if you look at that, Amazon doesn't actually give you one of those things either. But again,
Amazon definitely does. I mean, they give you, they have, it's very obscure and hard to understand, but they do have, what money you get back if they breach their SLA.
yeah. Again, these are the sort of things that we will have individually with customers, and we can absolutely go sort of address those issues. At this point in time, what customers are enamored by is the architecture and what it offers them. I'll tell you this, when the earliest customers we had, we talked about the fact that we are running this infrastructure for them. And I asked a couple of times, you understand that we are actually doing all of this stuff and we are updating your software. You're okay with that, right? And then this particular customer was a senior director of infrastructure, a large company, says, yeah, I get it. None of us want to do this, and we are quite happy with you doing it. And we are completely comfortable until you mess it up, and then we'll have a conversation. I'm happy to say we have still not had that conversation, and we look to continue to do that, right? So at the end of the day, all of these SLAs are wonderful, but what really matters is how fast can you respond to a customer need or a customer issue. And to date, it's been fantastic. And really, it's been fantastic not because we're a startup and therefore incredibly focused on customers. It's really because you've built both an architecture and a process which is in a different way, in a completely different sort of design point than what exists today inside the data center.
Other questions?
What's your other requirements for customers before this appliance comes on site? Network, ISP, bandwidth?
We think of it as like power, cooling, and then a few network ports. So yeah, what we look for is just that, power, cooling, few network ports, and then we would ask for some IPv4 that has poked holes to our front end. So that's really what it is, a couple of IP addresses and good to go. So pretty simple. We try to keep the full experience from even contracts all the way up to install and process to be as zero touch as possible.
So you highlighted that you guys are still fairly early days at the moment. So how do you provide this service in terms of global locations? And you also mentioned earlier on about who's providing your hardware. Are they also providing, when you do have to have an engineer go on site to do swap outs of kit? You doing that yourselves, or are you?
We do that ourselves, and we own that as a business. It's our problem, and so as we scale, there's plenty of ways to work with partners to be able to enable that break fix. A key part of this is the fact that you do not have to go react to a failure, right? So the failure reactment, and spinning disks will die, network ports will go offline, but we can go react to this in a way which is more efficient from our perspective and without affecting a customer SLA, if you will. Today, you're local here in North America, but there's no reason for us to be limited to that. In fact, we fully expect our customers to drag us outside North America into other areas very quickly. And so as a young company, you have to start someplace, and you start where you live.